Yeah. Yeah.
Perfect. All right, everyone, thanks for coming. We're very lucky to have Nika Haghtalab here. Nika is an assistant professor at UC Berkeley. Before that, she did her postdoc at Microsoft Research New England and her PhD at Carnegie Mellon. But I think most relevant to this audience is a homecoming of sorts to her. She was an undergrad and a master's student here at U Waterloo. So to welcome her back, I turned on the snow just for old time's sake. Yeah, Nika is truly a very versatile researcher. She's done important contributions in so many areas. You know, some people are experts in algorithms. Some people are experts in econ CS social choice type things. Some people do theory ML. Some people do empirical ML. Nika is the whole package. She does stuff in all of these areas, and she's been highly recognized for it in many places, including dissertation awards from both CMU as well as the SIG-Econ community, best paper awards at EC and Europe's, things like the Sloan Fellowship, Schmidt AI 2050 Fellowship, Google Research Scholar, all these different things. She's been accoladed across a variety of different communities. And what I really appreciate about Nika beyond her research contributions is just how she's able to give back to the community. For example, she's chaired ALT this year. She's chairing COLT. I hope you all have submitted your reviews by now. And she's also involved in what I think is very important, the Learning Theory Alliance, which is she founded it. It's an organization intended to build more of a community around learning theory, which is something very near and dear to my heart. But without further ado, I'll pass it off to Nika.
Thank you so much. Thank you so much for the introduction and for the invitation. It's really nice to be back. I left Waterloo in 2013. It's been 12 years. But it's great to be back to a place that I feel like sort of taught me how to do rigorous work in a way that I really appreciated sort of doing mathematical thinking for, broadly speaking, for machine learning. So it's really an honor to be back and happy to see a lot of old faces and a lot of new faces and faces that I have forgotten the names and faces I remember the names. So hope to see you and talk with you guys more throughout the day. At Haghtalab, I work on a lot of different things, and the talk I'm giving today is about a theory of multi-objective learning. This is a very rich area where there is a lot of empirical work, a lot of theoretical work. And throughout this talk, this is a theory talk, of course, but I'm going to actually highlight a lot of connections to things that have come up more and more recently in the practice of machine learning, as well as the theory of machine learning. I know this is a theory seminar, but I just, out of interest to know who is in the room, who associate most with theory of computing in this room? And are there people who associate themselves with more on the empirical, the practical side of AI or other fields? And anything else that areas that people typically think themselves as being a member of? Number theory, okay. So theory, math. Okay, cool. So I'm not sure if I will have any insights for number theory, but I hope to have insights both for the theoreticians in the audience and for the empirical people in the audience. So let's get started. I want to first. Somehow this is not working. Okay. I want to first start by actually acknowledging my co-authors. This line of, like, the talk I give today has, it's not about a single paper, it's actually about a line of work. I will highlight different pieces of it. And this line of work has been done with collaboration with a lot of really amazing co-authors and collaborators and students and postdocs. This wouldn't have been possible without their contributions. So kind of the premise of the work and multi-objective learning is that more and more recently, we think about, especially when we think about machine learning and artificial intelligence, we're thinking about moving beyond models that are designed for very specific tasks, for example, translating one language to another, to models that are a lot more general purpose and can sort of simultaneously adapt themselves based on the need that we have. So these are models, for example, that you have seen with generative AI, being able to, both translate one language to another, but also to be able to generate text that is more about summarizing certain texts, or maybe about providing predictions about other types of texts. So these are much more general purpose multi-objective types models. And in recent years, we've been really thinking about how can we actually get this type of multi-objective models that can have many different properties all at once and excel at many different tasks. And in some way, the way I like to think about multi-objective learning is that traditionally, when you thought about machine learning, you wanted just to have one predictor. This is a function that takes as input some feature vector, and as output give you, for example, a label, like whether this image includes a cat or a dog, and you want the average accuracy of this model to be high. That's the traditional perspective of having average accuracy. And we're moving beyond that to having that model that, of course, has good average accuracy, but you also want it to be perhaps well calibrated. So whenever it predicts, positive, it truly means that it should be positive. And whenever it thinks it's negative, it truly means that it should be negative. Or we want it to be not just average accurate, but also average with per type of sort of input that it's looking at. So if the data is coming from medical data where you have specific age groups or gender or race, you don't want this to be average only, accurate only on average, but also you want it to be average for young women between ages of 18 and 25. You want it to be accurate for children, and you want it to be accurate for people who may have other conditions. You want this model to be aligned with human values, whatever those human values may mean. You might want it to be safe and secure, and to be able to sort of meet many different types of constraints and objectives that you're thinking about. So to me, multi-objective learning as a whole is going beyond the traditional perspective that I have just a single loss function which evaluates my model, to thinking about many different forms and things you want out of your model. Now, while with generative AI, we are seeing some advances to this in terms of models that are definitely a lot more capable. I'm sure we've all been working with ChatGPT or other generative AI technology. That means that we have are starting to see truly multi-objective models coming up. We have good performance for many recognizable subpopulations. We have perhaps good performance even on adversarial and unpredictable environments to some degree. These are the things that we're hoping to get. And I would say that on the front of capabilities, we have actually managed to definitely use larger data sets and larger models to create more capable models. But in terms of reliability and fairness, we have hit significant bottlenecks in the sense that even when we train models to be quote unquote safe, so that they don't answer to malicious requests that you send them, we see persistent jailbreaks where bring the model out and the model starts behaving unpredictably again. In terms of fairness, again, we're seeing unequal performance where on average these models do quite well, but then you deploy them on young women from ages of 18 and 25 and they no longer do well. So that's because in general, I find that to think about reliability, fairness, and in general, like multi-objective property, you need to really be thinking about mathematical and provable guarantees rather than the good feeling of, yeah, my model is performing kind of nice on average. So for this talk, we're going to really embrace that mathematical provable guarantees and also algorithmic framework for how to train model, how to curate data sets. If you wanted to, from ground up, think about how you would imagine a theory of multi-objective learning. So the questions that we will be talking about are, how should I design learning systems that have provable multi-objective guarantees from ground up? What is a mathematical framework for capturing multi-objective guarantees in general? And then what are some design principles in terms of algorithmic toolkits, optimization toolkits, and even data curation toolkits that are necessary for this? So this is all foundations of multi-objective learning. What this talk is going to look like is I will give you one unifying framework, like a mathematical framework for how I describe multi-objective learning for this talk. That's just one, but I find it to be quite unifying because it brings many different perspectives from many different communities together under one umbrella. Then I'll talk about the toolkit for designing algorithms with multi-objective guarantees, both in terms of data curation, which means on-demand sampling, and also optimization techniques, which are algorithmic optimization. I give you examples of how you can.
What did you mean by data curation? I missed that phrase you had thrown because I had a different interpretation.
Yeah, so data curation means that if you have possible data sets or distributions to choose from, where do you choose to get your data? So that's an example. I will make it a little bit more clear mathematically, but in general, like imagine that this is actually in University of California, San Francisco has a medical school. Like one natural problem they deal with is that they're trying to train models that are predictive of whether, the next 5 years you're going to develop a risk of heart failure or kidney failure. And they don't have perhaps a lot of data just from California, but they also have data from Massachusetts, from Georgia, from different places. And they want to know when should they actually go outside of California to curate their data from other places to improve performance in California. So this is called data curation. I'll give a mathematical definition of it in a few slides. It's kind of vague, so.
When the data is just humongous items in the data are just plain wrong.
Sorry?
Are just plain wrong.
The data is wrong.
Yes, I looked at an issue with Google. Talk to the person who is responsible for writing their stuff on this, and issues are, you have authoritative sources saying X, multiple authoritative sources saying X, but somehow in social media, there are far more people saying not X, and it's wrong. And the authoritative sources give reasons for why the thing is wrong, and yet the AI summary is that it's right. So, and this will get into, I assume this is an issue that is one hardcore issue.
Primary concern we try to address with this work, even though robustness in general is, like, I think the way we think about this is that your data might not necessarily be like misinformation or wrong in that sense, but it might just not be of the right quality or relevant to the task that you want. Especially with multi-objective, I was just saying, you're trying to improve the prediction perhaps on women ages 18 to 25. Why do you even expect that the data from men ages 18 to 25 should be relevant? We see that it is, but instead of a human expert or a domain expert kind of trying to decide when the data is relevant, we're going to talk about algorithmic toolkit that can tell you where the data is relevant. So let me defer some of this question about what it means to curate your data sets to when I actually introduce the notion of on-demand sampling in a few slides. But this is kind of the outline of the talk, and we can, of course, go at different speeds depending on what you guys are interested in seeing. So let me start by this unifying framework for multi-objective learning. At a high level, again, the context for thinking about multi-objective learning is that we want learning guarantees that hold over the different application areas, different domains, for different stakeholders, and even different sort of individuals' needs and limitations. So in the context of like the UC San Francisco that I was talking about, you're trying to train an actual medical predictor, like a disease predictor, risk predictor. You might have data and hospital that's coming from different hospital systems, from different states, from different stakeholders. And you want to also have predictors that then can be deployed in different branches of these hospitals and different areas within US, Canada, and the world. And the idea is that what you want is that you want to enable these learning processes that can satisfy these multiple objectives of, maybe having like a children's hospital or a hospital that's specifically focused on renal failure or medical center that's specifically for children or women. You want to be able to satisfy all the needs of these different domain areas for several stakeholders, but from collectively fewer resources than you would have needed to do if you didn't actually try to bring these objectives and resources together. So the way I think about this is to think about fine-grained guarantees. So what that means is that, for the rest of this talk, we think about a scenario where we have k different distributions. You can think about this as possible tasks or downstream domains. A distribution d1, d2 to dk, from which we can actively sample from. Now, when I say a distribution in the context of machine learning, a distribution is a distribution over pairs of feature vectors. We often call them x's, and labels, which we often call y's. So a feature vector could be, the entire medical history that I have that the doctors can access. And the label, y, could be whether or not I'm likely to develop a certain disease in my life. Or whether I have already developed it. We also talk about having many different loss functions, R loss functions. We call them L1, L2 to LR. And a loss function is a function of the feature vector x, the label y, and also the predictor, that the function f. And you can, for example, think about a scenario where the loss function is just the accuracy. So whether that function, when it looks at my medical history, realizes that I was actually high risk for developing heart or renal failure or not. And that would be, for example, the binary indicator of y not being equal to f of x. That's the most common loss function you see in machine learning, especially. But you can also think about other loss functions. The loss function I have here, y minus f of x, times the indicator of x being b. That's called a calibrated loss function. And the idea is that you want your loss to be small, conditioned on the value of the prediction. So if my predictor says that I fall in the 70th percent, that I have a likelihood of developing a disease in 70% chance, then for all those people who are predicted to have 70% chance, we want the error not to be really large. Like, we don't want them to all be sort of receiving the wrong label, all of them. So these are different loss functions. For the purpose of today's talk, I think it's just enough if you want to think about the binary losses as being one of them. And lastly, when I have a loss function, I can think about the expected loss as this capitalized loss with a subscript of the distribution, which is just the expected value of the loss on the distribution. So in general, in plain old machine learning theory, what you're interested in is to find a function f that has small loss in expectation over your underlying distribution. This is often what we ask for. For a given distribution di, for a given loss function, usually the binary loss function, Lj, we want the expected loss of a function we have learned to be small, as close as possible to 0. When we are thinking about having multiple distributions and populations, we want to say that this loss is small no matter the distribution and no matter the choice of the loss function that we are given. And in some way, if you can do this, this is a proxy for saying that you're uncovering a universally good predicting model f that works no matter the loss function, no matter how you penalize it, reasonable ways of penalizing it, and no matter what populations it's deployed on. This is not always possible. For example, it's possible that your distributions are completely disagree with each other, or the loss functions are incompatible with each other. If that is the case, what the goal usually becomes is called agnostic learning and machine learning theory. Let me see if I can move this. I don't seem to be able to move it horizontally, but I can move it vertically. Okay. So when this is not possible, you try to do as well as is possible. And as well as possible is usually compared with some function class h that's given to you. And you just want to say that I want to be able to do as best as the best function in this class would have been able to do. And that's just the best in class. This, especially the second line, which is slightly more general, is the goal of the rest of the talk. If you have a question about this, this is the perfect time to ask as to what this means and why we're doing it this way.
Questions about jailbreaking briefly. I'm wondering, I thought there's inference time attack based to this structure, and traditionally we use, for example, adversarial training to address inference time attack into this structure.
Yeah, adversarial training is actually one way of doing this min-max. Once I talk about the algorithmic perspective, I'll highlight how adversarial training is essentially trying to solve the min-max equilibrium. This is one way of creating models if that are robust in a provable way when you can actually train these models. Other questions? Okay, so I just want to say that, okay. I somehow it thinks that I'm clicking on that thing and I don't know why it's doing that. Okay. I just want to say that while this is the model that we are working on, often people want slightly different losses whenever I give this talk. Like sometimes people say that I want to personalize my solution, so like maybe I'm willing to have different loss functions fi's per distribution di. So if you want to do that, it's a simpler thing, and then we call this a personalized thing. You can still like our algorithms of course work here, and we have a pretty good understanding of what is it that you can do slightly better in that setting. So if you're interested, talk to me offline. There are settings where you want something that appears even slightly harder, where you say that I want not only to do compared to best in class, but I actually want to do as best as possible per distribution. And that is a slightly different way of thinking about min-max. Again, this is the type of thing that even though it doesn't look like the function, the loss I gave you in the previous or this one, we actually know how to use the framework of multi-objective learning to solve these problems and achieve the state of the art, improve in fact on prior works. So if you happen to be one of the people who likes these better, just to tell you that you still will benefit from this talk, even though they don't look exact. Yes.
The second one, not even this or this interpretation. Like you want to have a single function that on every single distribution.
They exist, yeah. So when this is usually comes with assumptions. So people who work on this sometimes call this multi-group pack learning. I'll give you a citation in the next slide. And it comes with assumptions of the form that either you have realizability, which means that there exists a function, just that function could have been really complex, and you want to learn it without paying that complexity. And in other cases, there isn't any single function that would have done well, but you essentially say that the best function per distribution would have not disagreed too much with each other. So the second line, whenever people look for this, they have additional assumptions, which is exactly why those assumptions together with multi-objective learning can make sure that you're at this. Okay, so this was just in case you have other things you want out of the system. You should still listen to the rest of this code because you have something to do.
Basic thing, the whole thing is basically you're trying to figure out when you're in trouble by making things too general. And that's, we're putting math around it.
Exactly. Well, we are saying right now, we're just giving literally a loss function. We're just saying that in traditional machine learning theory, you don't have these two maxes. You don't have these two maxes. And we have developed theory of machine learning for decades. Starting with in 80s and early 90s, we figured out how to solve these in a provable way and what are the algorithmic constructs for them. What we're doing today is that if I have the max, can I actually build on the theory that for decades we've been working on so that we extend those provable computational and sample complexity and everything else to this more complex, more general set. I said that this is a unifying perspective. Let me just put a bunch of things on the slide here. While I don't have a lot of time to go through this, in recent years especially, there have been instances of people wanting this type of a min-max objective without even realizing that that's what they want. Inspired by fairness, collaboration, federated learning, calibration, and many other fields. This is just an example of groups of people who are actually coming from theoretical computer science background primarily, with maybe one exception, or two exceptions here, that have been trying to do this. And if you actually go into the practice of machine learning, we talked about adversarial training, there's a lot of work that at the end of it, they're actually looking exactly for the loss function activity. So the perspective that I gave in the previous slide is actually more general from all of these. And one nice thing is that if you can figure out how to solve the problem I gave you in the previous slide optimally, you have essentially solved all of these problems. That's exactly why I think this is a very nice unifying perspective, because this is not about one instance of a problem that for one application that you find that you need this min-max perspective, but that generally we are in a multi-objective world and we need to understand how to do multi-objective. Sort of continuing on the answer I gave to Ian, one way to think about this is that traditionally, we are thinking about one distribution, one loss function in theory of machine learning, and we're only going to, essentially, we're extending it to multiple distributions, multiple loss functions. For the rest of this talk, I'm just gonna assume you have a single loss function, multiple distributions, because most of what I say will just translate and it's easier for us notationally. So we are trying to solve the thing that's in the right-hand box, but of course, we want to solve it by building on the theory that for decades you've developed on the left-hand side, both in terms of algorithmic techniques and also in terms of comparison in terms of the guarantees. So for those of you who need a quick refresher, I'm not going to actually say much about this, with an exception that this is a very well understood paradigm. In particular, two things that are very well understood about it is that the number of samples you need from this distribution in order to provide this type of guarantee is defined by something called the BC dimension, and 1 over epsilon squared, where epsilon is how accurately you want to recover this. And this is a minimax bound, so it's tight. And also that's in terms of sample complexity. And there is essentially a single algorithm that achieves this minimax bound, and that's called empirical risk minimization, or ERM, which essentially means that you have a loss function, just go optimize it on a sample set. So this is very well understood. What is not well understood is that what is the algorithmic paradigm here? Is it still ERM? And how much samples do you need from here? So we are going to answer both of those questions essentially about this. And we'll do our comparisons based on this. So that's the unifying perspective that I wanted to give. Now, let's actually move on to understanding how the toolkit for this will work. Yes.
For the previous example, you have k different distributions and that's the difference. Can we just reduce it directly to the left by defining uniform distribution over k? Let's see what happens.
Hold on for a moment.
That's the question, so, the previous slide, if you go back, for the problem on the right hand.
Yeah.
There's an algorithm that we mentioned in the previous work, AFL, agnostic relationship. That is actually solving this problem exactly.
This is agnostic.
Yeah, So this one, I'm wondering now, what is the shortcoming of this approach to?
Hold on for a moment. Yes.
Maybe this is a naive question. This just, is there a relationship with this formulation of multi-objective learning and like risk measures? For example, they use it for portfolio selection. So like, especially in the case that we have several distribution, the fact that you're basically optimizing maximum of expectation with respect to several DIs looks very much like a single risk measure.
I feel like I don't know enough to state a claim here, so maybe we should talk offline about risk measures there. Once you see how we do things, like it's a very natural thing that we're going to do algorithmically, and then we can see what that connection is. Okay. Okay. I wanted to say a few things. So this is actually directly related to what Severin was asking, which is that you have k different distributions, just define the uniform thing over that. What happens if you do that? Actually saying that what you're going after is to be thinking about average accuracy over the mixture of these uniform mixture of these things. So what's the problem with this is actually problematic, not just theoretically, it's problematic in practice as well, which says that the reason this is quite ineffective is that even if you look at your optimization, average accuracy is not a good proxy for like minimum accuracy, or max error and average error are very different from each other, k-fold. And this is a problem for a couple different reasons. One is that if you're running an optimization, you just need actually many steps longer, like k-fold longer for it to converge, also in practice. And another thing is that a lot of times one of these distributions is of lower quality than others, and that becomes the bottleneck in a way that it doesn't And this bottleneck keeps changing. First, like focus on random distribution, it's not working, and then others. So as a whole, this perspective of thinking about average accuracy not only doesn't produce the right thing, but also even if you run it longer on larger sample sets, it does eventually converge to the right thing. It's just that it's not leveraging the fact that there are dependencies between these distributions in a way that we don't a priori know the dependencies and similarity and pieces. So whatever model we're thinking about, hopefully should be able to leverage and realize that there are some similarities between tasks automatically and then do better. So this is why I like to think about this as to solve this problem optimally, you really do need to think about where your data is coming from. Remember we said that we have distributions D1 to Dk, and you can sort of decide where to get samples from rather than just taking from their uniform mixture. So the standard approach of collecting a priori fixed size data set is what a lot of people have been thinking about. One of you mentioned the advanced federated learning, and in fact, most of this stuff that was on that previous slide, they fall in this category of quote unquote standard approaches where they don't try to actually shape their data set as much. And then they collect a fixed number of samples, or at least, something in a non-adaptive way. And then what happens is that this standard approach ignores the fact that distributions are related to each other or there's some shared difficulty or ease. And mathematically, you can show that with this type of non-adaptive data collection, non-adaptive meaning that you have a sample budget per distribution that's decided at the beginning before any of your samples are actually taken, the sample complexity of any algorithm is going to be k times the sample complexity of learning for a single distribution. So this says that both in terms of separate question and the other question that was being asked about federated learning, the problem there is that you really are blowing up your sample complexity k-fold, which, if you think about it, what this is saying is that without an adaptive protocol for data collection, multi-objective learning doesn't save data any more than learning like many specialized models for each of the tasks would have done. And this is particularly problematic when you think about robustness and reliability, or even multi-agent collaborations, when you just have that case large. So this is where on-demand sampling, or what Ian was asking, what does algorithmic data curation mean, is coming in, and it's actually in practice is one of the major important components of making multi-objective systems right now. Each company is deciding sort of where the data should be coming from and how it should be curated. And they have like each of them have like some kind of a magic formula that they are not releasing. This idea is that to effectively learn with multi-objective guarantees, the learner has to actively shape and curate the data set, not just scale the size of the data set. So it's not just about the scale of the size. We call on-demand sampling at a high level when you can generate training data from wherever you need it, whenever you need it. It's a form of active learning, which means that you're given distributions D1 to Dk. You can think about them as sampling oracles, and you actively pull them to get more samples from whichever of them you want and whenever. For those of you who are plugged into the practice of ML, this is related to sort of three paradigms of ML, modern ML in particular. One is self-generation, where you want to think about an algorithmic or a manual approach for filtering out some of the data that is self-generated by models. That's also a way of thinking about curating the data set in an on-demand way. It's also related to federated learning, like the way I was talking about, rather than just thinking about clients that exist and you get the average of the data. You want to actively incorporate data from different sources. And for those of you who are familiar with fine-tuning and other post-training methods, you can think about fine-tuning, like a single step of fine-tuning, as a two-level adaptive way of deciding where your data is going. I'm not going to go into the details of these. This is just in case you are interested in the practice of ML. I'm happy to talk about these offline. So now the theorem statement that we are going to be sort of looking at further is that if I allow on-demand sampling in this adaptive way, which means that if I collect my samples adaptively and actively from the different DIs, then there is an algorithm where the overall sample complexity is going to be log k times the number of samples that would have been needed for learning for a single agent. And this is kind of a higher level. In fact, if I were to write the real sample complexity, it's even nicer in some way, which is that in the top non-adaptive way, you should really be thinking about log of H as a complexity dimension almost, as the complexity of a class, and K as the complexity of your distributions. You are multiplying log of H and K together in the non-adaptive. In the adaptive on-demand sampling, you add them together, which is a huge saving if either of these two things is large. So I will talk a little bit more about what's written on the bottom of this slide. If you have any questions, let me know.
I'm sure you'll get into this, but like how adaptive does the algorithm have to be?
Yes, very good question. Let's talk about this primarily offline because we have some works there, and none of them are published, but I can tell you the round complexity of what currently is on here. It so happens that we're realizing there is a very interesting trade-off, which we haven't yet published and it's still in the works. So, yeah. Other questions? Okay. Okay, so we saw what on-demand sampling is defined as and what we can get in terms of a theorem statement. But let me highlight to you why, in principle, this is a powerful thing and it helps. I'm gonna not prove exactly the theorem I put at the bottom of the slide, but prove something that is a little bit worse than it, but still interesting. So optimization with on-demand sampling is essentially based on saying that when I look at that multi-objective sort of benchmark that I have written, I can think about this as the min-max equilibrium that I'm trying to approximate. What is a min-max equilibrium? Min-max equilibrium is when you think about a hypothetical game where one player, here the green minimizing agent, is trying to minimize a loss function over its action set, where action is a choice of a function and predictor. And then you have the adversary, which is the maximizing, who is trying to maximize this loss function over its choice of actions, where each action is a distribution. So essentially, this is a game where capital L is a game matrix that takes into account actions of player green and actions of player blue, and both of them get reward. One is it's a zero-sum game in the sense that one is the negation of the other. And a min-max equilibrium is literally this. Any choice of F and the distributions over maybe function class and distribution over distributions such that this is tight within X. That's called an X. For whom is min-max equilibrium new in this audience? Who was familiar with min-max equilibrium? Good. So for those of you who are familiar with min-max equilibrium, you also probably know that they were one of the early, I think, really interesting success stories of machine learning theory and economics connecting to each other through the works of people like Rob Shapiri, Yoel Freund, and others, where essentially the algorithmic way of coming up to this economic construct was done by learning theorists in an efficient way. Prior to them, people had thought about fixed point theorems, but in a less constructive way. So algorithmically speaking, if you are trying to actually find a min-max equilibrium, you have a choice of algorithms. And these algorithms fall in the following sort of category, where you assume that one of the players is playing something called a no-regret optimization. The other is playing either a no-regret or a best result. No regret, I'm not going to go into the details of this, but it's a very fundamental paradigm of learning in which you're trying to learn over a sequence while having sort of your average performance being as good as the performance of the best option in hindsight. And that's something we know is possible through algorithms like boosting style algorithms like follow the perturbator, follow the randomizer, and others. And best response just means that myopically you get the loss function and you try. So what we do know is that if you pick any of these dynamics where one player is no regret, the other player is best respond, then you do converge to the min-max. Now, why is this not plain old min-max then? It's because whenever you think about min-max, there is actually a game that you typically know what that game is. That's the L. Like when an economist thinks about a min-max equilibrium, they have literally a game table. In this setting, there is no game table in terms of it being written down. In fact, to even know this expected loss of a function over a mixture of these, I need to take samples to evaluate this. And this is exactly what sample complexity comes in, because the number of samples now relates to two things. One is that you don't know the game, so you need to estimate the game as you go. So that is, you take samples to estimate the game. So the quality of your estimator matters. And then each of these dynamics has some convergence rate. Some of them will take really long to converge. Some of them will take short time to converge. So since you keep repeating these dynamics, you also take additional samples per time step. And that's the second place where sample complexity. Let me give you a little bit more intuition as to how you would operationalize this min-max. So I'm going to talk about a situation where my minimizing agent is just going to be best responding and my maximizing agent is going to be no regret. What that looks like is that the minimizing or the best responding agent is given a distribution, which is a mixture distribution over these DIs. Let's say that mixing weights are essentially the alphas. And then it's what is best response? It's just the empirical minimization. So it takes some samples and minimizes the loss of attention. Now, what does my max player do? My max player is the no regret agent. It maintains actually those alpha I distributions. Those are the actions taking. The no regret learning algorithm has a probability distribution of a bunch of actions. And you can think about these as the proxy of how poorly a distribution DI has so far been doing on the solutions HT that have been outputted by the midpoint. Where is sampling coming in? Both of them actually have to sample. The mean player has to sample because it's doing empirical risk minimization. So it gets these mixture weights, but it has to sample according to the mixture weights. And the max player also has to sample because it's trying to keep a proxy of how poorly each distribution has been doing so far. So it has to take samples to know how poorly it's doing. It's adaptive because each of them looks at the actions of the other. So the minimizing player has to look at the mixture weights, which are the decisions made by the max player. And the max player is maintaining the mixture weights by looking at how poorly HTs have been treated. So this is why there are samples. This is why this is adaptive and on-demand sampling. And you can think about the number of samples here as to be just proportional to these alpha I weights. And these alpha I weights.
Does the alpha I sum up to 1?
Yeah, this is, they sum up to 1 because we've normalized them here. Other questions?
Does it make a difference in your analysis which
Not in what I discussed, actually not in anything I know. Okay. That's one of the beauties of this because it reduces to the first
Because assuming that the min clear problem can be like solved all of the time.
If it can, then okay, maybe in other words, some of the algorithms in this talk and in this line of work are called oracle efficient, which means that if you're given a polynomial oracle for the minimizing, then the rest of the putting everything together is efficient. Okay. Let me also just say that why does this work at a high level? The reason this works is I'm going to show that because it's very simple to prove that it works with slightly bad sample complexity. So let's do it together. Imagine that you're in this setting that there's this min-max benchmark is actually 0. So like there existed one function that achieves perfect prediction on every distribution. Then let's
Is this assumption like
very strong, I feel like.
Yeah,
It's-
it is very
It's not
strong.
always possible because there's trade-offs between different.
Right, so do you remember that when I defined multi-objective learning, I gave two definitions, one was relaxation of the other? This is the stronger assumption, while we are trying to solve the weaker one, this is an easier one to put on a single slide. So what does the sample complexity of this agent look like? This agent essentially comes up, it has a single distribution, it's just that distribution keeps changing. So I should be thinking about this distribution PT as a mixture distribution per time. And I can just treat it by saying that I know from decades of work how to deal with a single distribution. So I deal with it by taking that many samples, and then I will have a loss function that is at most epsilon prime. The maximizing player, I'm gonna be a little bit more hand baby, but imagine that it takes enough samples, and this is just a Chernoff bound, but it takes enough samples that for any given HT, it knows how well each distribution DI is doing. And then it uses these sort of approximate proxies to give a no regret out. What does it mean to be no regret? This is a definition of no regret for the max player, which means that these are the actions that the no regret player is taking. And this is a sequence that is observing. So this is the loss that on average a max player is getting over T times step. A max player is no regret if it competes with as well as possible with a term called regret compared to the best in hindsight. So if it waits around to see all possible H1, H2 to H10 display, and then pick a single distribution of them. This is called the no regret algorithm, and we know how to do this. So now imagine that we get this guarantee because we just plug in some no regret algorithm. So what does this help us? If you run t long enough, which is log k over epsilon prime squared, this term becomes just an epsilon prime. This term is per step less than epsilon prime, so the entire thing is less than epsilon. Now, let me move the epsilons around. What essentially is happening is that I'm getting a distribution over H1, H2 to H2. Just take a uniform one out of all the possible ones that I generated by the player. This is the max error of such a complex classifier. And this max error is now proven to be less than 2,000. So this is how you prove that you just learned a function. It's a randomized function. It's coming uniformly from the choice of H1 to HT that has epsilon, it has multi-objective guarantees. Note that the sample complexity is not the one I promised you. It's actually this times this, more or less. So it is log k times log h over epsilon to the 4. The epsilon to the 4 is unfortunate, it's not optimal, but the log k times log h is what we were going for instead of multiplying k. So this succeeds in most things except that epsilon. Any questions about this?
Where is the H bar T appearing in the mechanism? Where is it used H bar T?
H bar T is the uniform, it's a random selection of H1 to H2. So H1 to H2 appears in the mechanism. H bar T is like random function uniformly chosen from H1 to H2.
But at the time T, do we use H bar T for?
You use H1 to HT minus 1. Other questions? Okay, let's see, how are we doing on time? Okay, we don't have a lot of time. We have two options. I can tell you a little bit more about how you can actually solve this optimally by giving you some pointers so that epsilon to the 4 becomes epsilon to 2. Or I can say that we've learned enough from this and enter sort of the closing part by telling you some other interesting things that have nothing to do with sample complexity of this specific problem, but they sort of open up to other more interesting algorithm questions that you might be interested in talking about. Let's see, who wants to see more of this? Okay, who wants to see more of something related to it, but not exactly this? So the second movement. For those of you who want to see more of the first, you are seeing it by me going over my slides. You get something, the right way of doing things. This is actually quite interesting. I think mathematically is really, really cool. So for those of you who do want to see more, I'm happy to like talk with you after, this talk is over. But there are ways to essentially improve the sample complexity in a really cool way.
That's all Sapir needed to really understand.
Yeah, Christopher is so fast that he already knows how to show this already. Okay, so let me start wrapping things up a little bit. By, sort of going back up the stack of multi-objective learning and why it's actually interesting to do theoretical work here. Multi-objective learning has led to improved sample complexity for learning, and many, like we talked about agnostic fitted learning and distribution robustness. And given that this is a theory audience, I didn't show the empirical graphs, but this is actually the state of the art. Like the algorithm that is doing best theoretically is also truly the best empirical algorithm we happen to have figured out. So it's one of those instances where theory and practice actually match. So it's meant like real improvements in real systems. So it's really interesting to think about fundamentally sort of what you could do here, because the theory and practice bridge seems to be one of the smoother ones. There are many other important directions. We talked about sample complexity. There is a little bit of computational complexity. I'm happy to talk about it offline. But beyond that, I think there are some very interesting questions. And one is, what happens when these distributions we're talking about are actually controlled by different agents? Like we talked about how these distributions could be thought about as the patient's information on like, you know, Massachusetts General Hospital, you know, versus like University of California, San Francisco hospital system. So these are not just distributions that you can at will go and get. Like you actually have to get people to agree to share data with you because there's tangible benefits to themselves as well. So this becomes a very interesting question about understanding the impact of incentives. And let me give you just a tiny overview of if you want to think about this, where you should start thinking about it. In the sense that this becomes sort of not just an ML theory, it becomes a more algorithmic, more mechanism design type questions for those of you who are interested in economics and computation. In a way that you can think about this as you have agents. Each agent has some sample set of size and you want to decide how much samples you're going to ask each of these hospitals to give you. And of course, what they want is that at the end of the day, you're going to run some algorithm, maybe, or some other algorithm on the collection of data. But each agent, what they want out of the system is that they want to get good error for themselves while doing as little work as, or like giving as much data as they need to. And one funny thing is that, let me like maybe formalize that slightly more. It just means that what are some unreasonable ways of asking people to give you data? One unreasonable way of asking them is to ask them to give you data that is more data than they would have needed to solve the task for themselves. Why should they give you any more data than is necessary for them? So that kind of says that you're not rational in some sense. The other is if I ask them to give me data and I take one chunk of the data or some amount of it to use strictly to benefit some other agent and not at all benefit the agent provided the data. So that's again another unreasonable way. If you wanted to formalize these sort of the economic
You
translation,
assume these people know how to do it,
how to do it.
whatever you're doing. You say these people, they give you more data than could be used to solve the problem that they need. Do they know the problem they need, and do they know how to solve the problem they need?
Yeah, they often
You're coming from, we know how to do it.
Yeah, so the rationality part is actually something very problematic if you are not satisfying, because it's very easy for them. What they often do is that they have a data set, they already train something locally with the expertise they have, and they see that it's not very good. And if they give, another way to think about it is that they're giving you the entire data, and you're doing even worse for them. And then they really don't want to actually be part of your system. So this is something that happens. We've seen it not just for data sharing, but in general, like there are matching problems that hospitals have faced where they pull out of these, or they never join often to these multi-hospital systems because they don't trust that they will get a better beneficial outcome for them. So this is.
Getting the best possible answer is not the high priority thing for these groups.
Sorry?
Getting the right answer is not necessarily the high priority thing.
I think for them is the trade-off. So they think that I want the right answer, and I'm willing to actually, give you more data if you give me the right answer. But if you're not going to give me any better answer that I could have done by myself, I'm not going to give you. This is the way to think about this. Formalization of this, for those of you interested, is that you could say that a system is rational if whenever you can provide the learning guarantees that somebody wants, it so happens that the amount of data and they should provide should be less than what they would have needed by themselves. There's also stability, which is the formalization of second part. For those of you familiar, this is more similar to what is called like Nash stability, where you say that every agent's constraint on the error should be met, but also that if you ever unilaterally reduce someone's share of how much data they should give you, their own accuracy constraint should be invalidated. Otherwise, they would defect by giving you less data. And let me just say that these matter in practice. I was just like talking, like answering Ian a little bit, but actually in real data sets, it's really unfortunate because both of these are not met, and they are not met in really like severely, in the sense that currently the reason some of these federated systems aren't completely breaking up is because agents aren't given the permission to break up. Like if Google is using your data, you're not allowed to opt out. And so those systems are really fine, but if you're trying to bring hospitals together to share medical information, they're just not coming together because of this. This graph is showing that in very natural data sets, something like 60% of agents think that they can unilaterally like drop their contribution to almost zero and still free ride. It's called free riding problem of federated learning. So it's a severe problem because if even a fraction of those agents do free ride, the system breaks apart, like it doesn't converge for others. What I wanted to just say a little bit is that if you are interested in this, it's good to know two results, I think, that highlight why it's important to do algorithmic work here. The first is to say that there is a price to actually providing rationality and stability guarantees. Like one way to think about this is that imagine you have an agent with a very generic data set that's uniform over the entire universe. And then you have these specialized agents that are kind of like on some corners of this data set. Then in some way, the optimal way of collaborating for these agents sample-wise is for the generic agent to take all of the data samples, because their samples are somewhat universally helping everybody else. On the other hand, the sort of rational thing is that the person with the most generic distribution shouldn't do any work, because everybody else, if the constraints, the accuracy constraints of all other agents is met, the generic agent's constraint is also met. So they're not, the agent that is that's actually critical. So they shouldn't be doing any of the work themselves. So this kind of a duality essentially is the problem, that if you sort of change more or less, go based off this constraint, this picture I drew for you, you will lose everything you gain from multi-objective learning, or in fact from collaborative learning, by showing that in some instances, the total number of samples that you need in a rational and stable allocation is k times the number of samples that you would have needed for the optimal collaboration. K being a number of agents. So you lost all that, k to log k that you improved. Here, there's a lot of room for a platform design. Platform design here means that a platform who might know more about how different tasks relate to each other, as opposed to knowing how to solve them, just knows the relation between them, is able to reduce this price a little bit. Unfortunately, not all the way back to something that's more like logarithmic or a constant, but still to some smaller polynomial. And this is done through something called Bayesian persuasion, where essentially the platform has some information and selectively reveals some of this information by making recommendations of the form, you should contribute, 10,000 samples. you should contribute 5,000. And you don't know enough information to realize that, like you're happy to go with the recommendations that is meant to. So for those of you interested in multi-agent perspective here, I think this is a very novel, very interesting area to be working with. And it brings theory of machine learning, multi-agent systems, economic and computation together. And I think it would be really interesting to stop you. Just wrapping up a little more, I am not going to go into the details of other problems, but another question that I think is relevant to the theory of practical ML is, where do these loss functions even come from? We said that they're just given to us, but in general, like these loss functions nowadays are trying to approximate human preferences, and those preferences are really hard to express, and they're very complex and malformed. So modern ML is trying to sort of get those preferences in an active way itself. So thinking even what's the right theory for that, sometimes people talk about this in the theory of alignment of generative AI. It's very much the type of question I'm going to be thinking about here. We talked a little bit about, UCSF might want to get data from many different places. We talked about how on-demand sampling is generally about algorithmic data curation. That is also very active and somewhat a nascent field. It's becoming more and more interesting in terms of how do we naturally think about algorithms for data selection rather than taking data as being fixed and algorithm space as being the only space for innovation. So these are all, I think, really interesting aspects of thinking about what a mathematical foundation for multi-agent and multi-objective learning looks like, which I think is a really nice set of questions for people in theoretical